Alright guys, we're here. We're finally at the most difficult part of this course, related rates. At least in my opinion, it's the most difficult part. Now, if you can understand this, well, congratulations, you're smart. Alright, so let's go ahead and get started. So, related rates problem. So what is the goal of this really? Is they want you to use implicit differentiation, or in other words, the chain rule, in order to find rates of a couple of variables that are related to each other, and they're usually related through time. All right, so what's happening is things are changing with time. You have two different variables that are changing with time, and we're trying to see how each variable is kind of changing, like at what rate. So I'm going to break these videos up into just example videos. So this will be the first example, then we'll probably have like 3 or 4 more. So let's do the first one. Alrighty, so suppose x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. Our goal here is to find dy dt when x equals 1, given that dx dt equals 2 when x equals 1. Alright, so we got to kind of break this problem apart here. The first thing we want to do is analyze that first sentence. Suppose x and y are both differentiable functions of t. So pretty much they're saying is x is a function of t and y is a function of t. So how do we write that mathematically? Well, we are used to things saying like sentences like this: f is a function x. Right? How do we write it? We write it like this: f of x. Right? We're using the same approach. And if my pen will erase, okay, it's really not erasing right now. Come on, come on, there it goes. All right, so I'm gonna write x is a function of t. So x is a function of t, and y is a function of as well. So with the related rates problem, all of them, what you kind of have to do is you have to take a step back and really think about what's going on in the background, all right? So if I were to draw this guy right here, x of t, how would I do that? I would kind of draw something like this. I would draw an x and y axis. Well, it'd actually be an x axis, and my output is x of t. So, wow, my pen is being really weird today. Okay, and the same thing goes for y of t. So I have y of t in the vertical axis and t in the horizontal axis. And what's happening is both of these guys, they're just some function. So something that we're not really defining precisely right now. Maybe they look like this, or maybe like that or something. I don't know. And what we're doing is we're finding dy and dt, dy dt and dx dt. So what is that? So dx dt is of the tangent points on this curve, just like this. Boom. Same thing, dy dt is just the slope of the tangent line of this curve. good. So we have a good base of what's going on here. We know that x and y are both functions of t, but the thing here is that y has some sort of relationship to t, somehow also related to each other. So this sentence right here, y equals x squared plus 3, is actually like an abbreviated form, like a nickname. So the full name that we should be labeling these guys are y of t equals x of t squared plus 3. I always put brackets here. You could put parentheses if you want. Doesn't matter. So you see, all I did was I took y and x, and I called them by their proper name, which is x of t and y of t. So now we have a little bit more sense what's going on. And look what the question is asking. They want us to find dy dt. So what we're going to do down here is we're going to take the derivative of both sides. So step 2, d dt. Same thing here. They're giving us something with respect to time. So I'm taking d dt of, I'm a fan of brackets. If you guys want to use parentheses, go for it. dt squared plus 3. Alrighty. I ran out of room. I wrote too big. So what does this equal? Well, dy dt is what we're solving for. So I'm going to come up here right now. Boom. So dy dt is what we're solving for. So that's just dy dt, right? And what I'm going to do on the right-hand side is I'm going to distribute this ddt across. So I have d of, wrong color. I don't know. I'm on blue. Come on. All right, whatever. We're sticking out now. ddt across. So we're taking the derivative of these two guys with respect to t. So let's see, the left-hand side is still the same as dy over dt. Notice how we don't have a real defined function for x, right? Like these curves I drew were just arbitrary. I just drew an arbitrary curve. So when I differentiate this, what I'm going to do is I'm going to use implicit differentiation. So remember, it's just like a result of chain rule. And I'm going to use it because the base here is not just t. It's some function of t. If it was just t there, I could use regular differentiation because it's in terms of t. So if I had something like this, t squared, t, this is not t, this guy is a function of t, I have to use the chain rule or implicit differentiation. Okay. So remember our rules for implicit differentiation. I'm going to take the exponent, drop it down, keep the inside function 1 from the exponent. I'm going to multiply this whole thing by the derivative of this inside function. So what is the derivative of this inside function? Well, we already said the derivative of this inside function is the slope of all these tangent lines. So this is the derivative of the inside function. So let's just dx dt. Here we have the derivative of a constant, so that just becomes 0. Alrighty, so we're almost done here. Let's just simplify. So we have dy dt times x of t dx dt. Because 2 minus 1 is just 1, so then alright, so we've simplified this thing as much as possible. Now where do we go from here? Well, now we have to go to the given of the question. Okay, so let's just reiterate what they gave us. In this question, they said, given dx, and they said dx dt equal when x equals 1. All right, so what does that mean for us? That means, let's go back here actually. Nah, it's a little messy. So what does that mean for us? Here's x of t, x, here's t. Make the same as before. So it looks like this. And here's y of t. Remember, these are just arbitrary curves I'm just drawing. It's more important that you guys get the concept down than anything. I think I just drew the same curve, just higher. Okay. So they're saying that when x equals 1, so here's x. When x equals 1, let's just pretend this is x equals 1. Let's just call this time t naught. Okay, is that okay with everyone? T0, t naught. So at t naught, x equals 1. So this point right here is t0, t0, 1. The derivative, the slope of the tangent, right here, is 2. That's what they're saying. And what they want us to find is right here. They want us to find what dy d same exact t. So t of 0. So what does that mean? That means if I come over here on my y graph, I'll have some value. So that'll be y. And our goal is to find what the slope of the tangent. I didn't want that color, but my computer's freaking out. What is the slope of this tangent at this point? Okay. So notice how to match. I'm using t naught for this, and that's all because of the information that's given to us. So hopefully that makes sense. So let's go ahead using the information that we now know. We can rewrite what's given. Of course, you don't have to write all these steps out when you're doing the actual question. I'm just trying to give you an in-depth look at what's happening. So I'm trying to find what dy for t naught equals 2 times x. We're just picking any x here. We're picking a certain x. We're saying x of t naught, right? When x of t naught, because we picked a specific, why is this, come on, there it is. X of t times slope at that point, the slope of the tangent at that point. So look, we're almost there. We have everything. So we have 2 times, what's x of t0? Well, we said x of t0 is just 1. So we have a 1. Dx dt at this point, so the slope of this point is 2. That's given to us, right? Is 2. So this means dy dt is just 4. T of this tangent line is 4. So there's a lot going on here. It's helpful with these problems to really break down in your head or on paper these graphs. All right, they're never gonna give you these graphs, but you want to start thinking about how are these x and y or whatever variables they give you, how are they related to t, and how do they change with t? And that's why it's useful to draw these graphs. Sometimes the graphs will be what these graphs actually look like. So hopefully that gave you a good understanding of what's happening here. I made it a little long-winded just so you guys can understand the background of this question, what's actually happening, instead of just throwing a bunch of algebra on the page. So we're going to have a couple more examples in upcoming videos. I'll see you there.